Fusion methods are of great usefulness to the chemical microscopist, both in the study of industrial problems and in pioneering research. Many of the compounds to be shown were studied in research problems active during the past few years in the microscopy laboratory of the Armour Research Foundation. Relatively simple and inexpensive equipment is required. A hot bar is useful for quick heating of a preparation to any temperature from 30 to about 250 degrees centigrade. Any microscope can be used since only low-power objectives are required. Crossed nickels or crossed polaroids are helpful. The Koffler Hot Stage is a necessity. This carefully designed and calibrated stage is used for controlled heating experiments and for accurate melting point determinations. The application of fusion methods includes all observations made during heating of a few milligrams of the substance on a microscope slide, during solidification of the melt, during cooling of the preparation, as well as observations on the crystallized material at room temperature. Fusion methods are perhaps most useful as a means of quick identification of an unknown, to determine whether two given substances are identical or whether a given sample is pure. They are also useful for the determination of composition diagrams and as a means of preparing good crystals for determination of the optical properties. Here we are about to see one of the simplest operations, sublimation. A small portion of the material is heated on one slide so that the sublimate condenses on a second slide above it. These crystals of mercuric iodide are typical of the type of sublimate obtained in this way. Sublimation is also useful as a method of purification, and the next demonstration shows a technique which can be adapted to the preparation of several hundred milligrams of pure material or to the formation of large single crystals, such as might be required for optical crystallography, goniometry, or X-ray diffraction. A small quantity of the compound to be sublimed is placed in the sublimation block. A clean cover glass is then placed over the opening in the block, and then the block is placed on the hot stage. As the hot stage is slowly heated, well-formed crystals condense on the underside of the cover glass. Here, the sublimate is being photographed with slightly uncrossed nickels. The micro melting point can be determined quickly and precisely using the Koffler Hot Stage. A fraction of a milligram is first placed on a clean microscope slide. A clean cover glass is placed over the crystals. The preparation is then placed on the hot stage. A glass bridge and a glass cover plate are next placed over the preparation to distribute the heat more evenly. The stage is heated rapidly at first, but at a standard rate of 3 degrees centigrade per minute in the region of the melting point. The actual micro-melting point is read on the thermometer at the instant the last crystals disappear. The appearance of crystals as they grow from the melt is also very characteristic of any fusible compound. Here, a few milligrams of TNT are placed on a microscope slide. A clean cover glass is placed over the crystals, and the TNT is melted on the hot bar. The preparation is then observed as it cools on the microscope stage. This is the supercooled isotropic TNT melt between crossed nickels. The supercooled and the crystals grow very rapidly. Here we see TNT crystallizing from a melt which was seeded before significant cooling occurred. Sulfur has large flat crystals with stepwise 90-degree angles. Para-prime DDT, the insecticide, grows first as needles. But as the temperature falls, the crystal habit becomes more compact. Lauric acid has a formless crystal front, quite different from TNT, DDT, and sulfur, but closely resembling that of other fatty acids. Using these same fusion methods, we can observe that many compounds show polymorphic transformations during cooling. Since a transformation is a result of rearrangement of the atoms within the crystal, a new lattice with new optical and geometrical properties result. These changes are readily apparent under the microscope as changes in polarization colors. This is illustrated first using benzotriazole, which grows in much the same manner as para-prime DDT, although much more rapidly. As the temperature falls nearly to room temperature, an unstable polymorphic form suddenly nucleates at the interface between the melt and the stable form. The unstable form then grows through the melt, although the stable form also continues to grow slowly through the crystals of the unstable form. A dark band of pseudomorph is observed where the transformation occurs. Here we see the yellow high-temperature form of mercuric iodide, illuminated with ordinary light rather than polarized light. The low-temperature red form has nucleated at several points and is slowly replacing the unstable yellow modification. Next, we see cholesterol acetate, which crystallizes rapidly as an unstable liquid crystalline modification. The characteristic softness of the liquid crystalline phase is shown by pressure on the cover glass with a needle. On further cooling, however, spherolites of the stable modification soon transform all of the unstable form. Perret's oxyanosole also crystallizes in a liquid crystalline phase, stable only at high temperatures. Pressure on the cover glass shows the soft character of this liquid crystalline phase. Another view of this same modification shows the transformation to a solid metastable form. A second transformation to the room temperature stable modification occurs as cooling continues. Ammonium nitrate is shown here growing through the high temperature, isotropic and therefore invisible polymorphic form. Another field of this same preparation was chosen to show a second transformation, which occurs at a lower temperature. All of the experiments shown thus far have involved pure compounds. The next series illustrates the mixed fusion in which two samples are melted side by side on a slide so that the zone of mixing can be observed. This technique replaces the mixed melting point as an identity test and is also used for the determination of composition diagrams. A few milligrams of component A are placed on a microscope slide, covered with a cover glass, and melted. Crystallization of component A then occurs. Component B is then placed at the outer edge of the cover glass and melted so that it flows under the cover glass into contact with component A. On further heating, all of component B and part of component A are melted. Crystallization of the two components is then observed as the preparation cools. This composition diagram shows the melting points of the various mixtures of two components showing eutectic formation. Using azobenzene and bromocamphor, we will show how these two components crystallize in a mixed fusion. Here we see azobenzene growing from the upper right. The growth rate decreases sharply as the crystal front approaches the zone of mixing. The bromocamphor then grows rapidly to the zone of mixing, leaving a narrow band of eutectic melt between the two crystal fronts. After a short period of slow growth of each component toward each other, the eutectic finally crystallizes as a fine-grained physical mixture of the two pure components. This composition diagram shows the melting points of various mixtures in a system showing addition compound formation. TNT and 1-mononitronaphthalene will be used to illustrate this type of system. TNT grows from the right, and after digestion in the zone of mixing shows characteristic profile angles. These angles are best shown in another field of the same preparation. The addition compound next grows rapidly through the zone of mixing along the TNT crystal front. On moving toward the mononitronaphthalene melt, crystals of this component can be observed growing toward the zone of mixing. After a short period during which the two crystal fronts grow slowly toward each other, The eutectic between mononitronaphthalene and the addition compound can be observed slowly crystallizing. Finally, the eutectic between TNT and the addition compound appears growing from the lower right. Systems showing solid solutions between two isomorphous components are illustrated in this diagram. In the example chosen, the stable form of trinitrobenzene is isomorphous with the unstable form of picric acid. The unstable picric acid transforms almost at once to the stable form. This phase forms a eutectic with trinitrobenzene. Hence, the transformation stops at the zone of mixing. Trinitrobenzene grows rapidly to the zone of mixing, but slows considerably as it continues to grow through the picric acid. On further cooling, the unstable form of picric acid suddenly transforms to the stable form. With this view of the photomicrographic equipment, we conclude this first film illustrating some of the techniques and applications of fusion methods.